We have a sonometer wire. In this wire, a 5 kilogram mass is hung. It causes the string to vibrate with a fundamental frequency of 50 Hz. If the length of the wire is halved and another 5 kilogram mass is hung, find the frequency of the third harmonic. Okay, so let's get some background on these fundamental frequency and the third harmonic business. Alright, now we learned about stationary waves and we saw some distinguishing features between traveling waves and stationary waves. One of the main feature being that the stationary waves don't travel, they are stationary. And more importantly, we learned that stationary waves have these amplitudes which keep changing from particle to particle, and they have nodes and antinodes and everything. But there's one more important difference, and that is the following. If I have a string and I clamp it between two ends, and that can be done in many ways. I can actually physically tie it between two walls, or I can have a wire, okay, and I can fix it at one end, and then I can use two knife edges. So one knife edge over here, another knife edge over there, and the wire goes then over that, and then you have a pulley here. The wire goes on that pulley, and then I can hang some weights over here. And whatever it is, now this wire is stuck between these 2 points, and it's forced to vibrate now. Okay, alright, so let's say some mass M is hung over here, and this is not floating in air. You have some setup. This, by the way, is called as a sonometer. Okay, and you will learn what's the prime use of a sonometer, as you will see. Anyways, if I have a string that is attached between two ends, okay, it's clamped at two ends, you can generate stationary waves in these strings, but you cannot generate stationary waves of any frequency. See, the traveling waves, you have the choice to select your own frequency. You are the source, so you decide the frequency. Turns out that doesn't work with stationary waves. If you try to oscillate this particular string with any frequency you want, you'll get a mess. You will not get a stationary wave. Instead, if you oscillate it with some particular values of frequency, which we'll calculate, okay, if we calculate with those frequencies, then you will see a wave will travel this way, they'll reflect off from this side, and the two waves will interfere with each other, superimpose, and you'll give you this nice stationary pattern. Now, to figure this out, we can either use the equations to figure it out, or we can do it intuitively. And I like to do it intuitively. And the intuitive approach is, remember the boundary conditions. The boundary condition is that this particle is not allowed to oscillate. Okay, so that's supposed to be a node, and this guy is also supposed to be a node. That's the boundary condition. So the question now is, if this guy is a node and this guy is a node, and let's say that this length is L, that's the length of the string, what are the possible stationary waves we can have with these two boundary conditions? Well, I'm pretty sure you can think about it. Which is the biggest wavelength you can think of? Well, the biggest wavelength you can think of is a stationary wave that goes like this. The whole string oscillates like this. That's the biggest wave we can think about. Okay? So, let's analyze what's the frequency of that wave. Notice that from here to here is half the amplitude. Can you see that? From one node to another node over here is always half the amplitude. Okay, so in this example, the first wavelength, whatever the wavelength of this guy is, half of that wavelength, so I'll say lambda 1 divided by 2, lambda 1 is the wavelength of this guy, should be equal to L. So lambda 1 equals 2 times L. So what's the frequency? Well, the frequency, that's the first available frequency, we'll say, shortest frequency, is going to be V divided by lambda 1, that's V by 2L. Okay, I'm gonna box this. This is the shortest frequency. You cannot have a frequency smaller than this. You cannot have a wavelength bigger than this. So once we have this, between two nodes, you have one antinode. What's the next smaller wavelength you can think about? What's this next stationary wave pattern you can think about? And what we can do now is we can have one node in between. I'm pretty sure you must have seen this before, but so I'm going to derive it anyways again. And so we're going to fix one node over here, and we can have a wave that goes like this. And a little later in time, it goes like this. That's a second wave that's available, that's allowed. and that wave would have a new wavelength, and notice that that new wavelength of this wave is exactly equal to L. So I'm going to use lambda 2. I hope you can see it properly. Okay, you can. And that is exactly equal to L. So what's the new frequency? What's the frequency of this guy? Well, that frequency will be a little higher because the wavelength is a little shorter. Okay, so that frequency is going to be V divided by lambda 2, that's V by L. Notice that's 2 times the fundamental, this frequency, okay? And let me do the third one, and then we will generalize this. Third one I'll do with the red. What's the next shorter wave that you can think about? Well, in the first one I had just 1 lobe. In this I have 2 lobes. And we'll have 3 lobes. So we'll put 2 nodes in between. So it's gonna look like this. The diagram is becoming messy now. But if you concentrate, you should be able to get it. So if you look for this guy, you'll notice that the entire length L is more than a wavelength. In fact, it's 1 wavelength plus another half a wavelength. So in this case, you have 3 by 2 lambda 3. That's the wavelength of this guy. So 1.5 wavelength equals L. So lambda 3 is 2L divided by 3, shorter value. Okay. So the new frequency F3 turns out to be V divided by lambda 3, which is 2L3. Notice it's 3 times this frequency. That's 3 times F1. I think this is enough. So what you can see is now that you can have a frequency V by 12 or 2V by 12 or 3V by 12, or in other words, you can have in general any frequency which obeys this rule, NV divided by 12, where N is an integer. It has to be an integral multiple. So this guy is an integer. Ooh, interesting. So the difference is you have discrete frequencies over here, unlike traveling waves where you can have any frequency you want. There are some special frequencies available. Now there are names given to these frequencies. They are called as, these guys are called as resonant frequencies. So you should know the names because questions will use different names. They're also called as normal modes, resonant frequencies. They are also called as natural frequencies. All of them, all these names mean the same thing. Okay, normal modes. Anyways, we also give names to these individual ones. The smallest frequency that you can have, that guy is called as the fundamental mode or the fundamental frequency. This guy is the fundamental. This guy is called as a harmonic. Since it's second time, 2 times more than the fundamental frequency, it's called as a second harmonic. So this is second harmonic. And this guy over here is the third harmonic. Third harmonic. Okay? So if I say 7th harmonic, it means 7 times the fundamental frequency. So in this example, it would be 7V by 2L. Okay, there's another thing that you need to understand. We also use the word overtones. What's the meaning of an overtone? Well, overtone is a general name that we use. Anything that's not fundamental is called as an overtone. This is an overtone, this is an overtone, and all the other overtones. Now, overtones are named a little differently. Okay, this guy is called as the first overtone. So overtone is basically saying that this is the first frequency available that's more than the fundamental frequency. That's the meaning of the first overtone. So it doesn't care whether the first overtone is 2 times the fundamental frequency or whether it's 3 times the fundamental frequency. It doesn't care about that. Harmonic cares about that. So I hope you understand the difference between harmonic and overtones. Any frequency that's just above the fundamental frequency, that's the next available frequency, is called as the first overtone. But the first overtone doesn't have to be second harmonic. Sometimes you will see the first overtone is the third harmonic. Second harmonic will not be available. Okay? Similarly, this guy, third harmonic, notice that's the second frequency available above the fundamental. That's why it's called as the second overtone. This guy is called as a second overtone. So do not get confused between the third harmonics and overtones. Overtones are general names. Okay, they are general names. They don't tell you exactly what's the relationship between the higher frequency and the fundamental one. They don't tell you anything. They're just telling you first overtone means first available frequency above the fundamental, second available frequency above the fundamental. Okay, all right. But harmonics do tell you. If I say fifth harmonic, it does mean 5 times the fundamental frequency. But if I say fifth overtone, it can be sixth harmonic. That will be in this case. Sixth harmonic will be the fifth overtone. But it doesn't have to be in general. Okay, so I hope you had understood what this thing is. Please remember this one, and we'll use this to solve the problem.